chances. Went maybe as to like proper theory.
I don't even have to. I'm out of the loop.
I don't want to tell you. No one is next to that.
Yes, exactly.
Oh, really?
But that's what would seem interesting.
Exactly.
Sure. So, excellent. So, we're very pleased that Mark Thomas, who is carrying out a PhD with me as supervisor, is usually at London.
Yes.
So they came to give us a seminar about data we wrote recently, and titled Master Superspace Action for 3D S-Duality. Please.
Okay, so hello everyone. I met most of you already. I think there's a couple of people who I haven't, but it was good to meet you all. So as Adi was saying, Ricardo, and I have completed this paper about 2 months ago, titled A Master Superspace Action for 3D S-Duality. Oh, one moment. Get it started. There we go. So I'll just quickly say what I'm going to do and how I'm going to show what the outline of the talk will be. So I'll start by talking about what S-Duality actually is and sort of why we're interested in it. Then I'm going to go on to specifically talk about a paper that Adi wrote a few years ago, which is a bosonic formulation of an S-dual to Maxwell-Chern-Simons theory. Then I get to the bulk of what we did in our paper. So I talk about the superspace uplift of Adi's bosonic work, and then also how we extend that in the non-abelian direction. And then right then I'm going to talk a little bit about what I've done since finishing this project and what's writing that up. So to start off, talking about what S-duality actually is. So S-duality is a statement or an equivalence between two, or it's an exact equivalence between two quantum mechanical theories with particular ways of recognizing what the S-duality is. The specific or the particular flavor of what you see in S-duality is that a coupling constant in your theory will be reciprocated, it'll be flipped on its side, and so strong coupling in one of these two theories will correspond to weak coupling on the other side. Particularly within any given quantum field theory, you will define what is called electric and magnetic data, which correspond to your electric equations of motions and magnetic equations of motions. And the idea is that under a duality mapping, an S-duality mapping, these two will exchange with each other. And particularly then, well, not just in the non-abelian, but also in the abelian actually, in order for it to count as an S-duality, we need that the gauge groups on either side of the duality are Langdon's joules of one another. So, so the nicest place to start is actually with Maxwell theory and in four dimensions. So what I have here is what looks like just two of the same thing written down, because it effectively is, but I want you to see this as two a priori distinct formulations of electromagnetism. And so on the electric side, so I have a static field, which I call the electric formulation, and on the other side, I have a different theory, which we call the magnetic formulation. And the idea is, so at the moment, I've only written the actions here, so this is classical at the moment, but the electric theory has sort of two main equations, which you'll recognize as Maxwell's equations on the left-hand side. And the idea is that the top one of those two, the classical equation of motion, is what we call the electric equation of motion, because if you write this down, it corresponds to Gauss's law on the electric side. And then the one beneath is the Bianchi identity, which has to be true given the construction of how we produce the electric curvature. And this is what we call the magnetic equation of motion. But what I want to point out there is that the electric equation of motion is a result of applying the Euler-Lagrange equations to the action, whereas the Bianchi identity comes about differently. It's a geometric fact of the construction. And then we have exactly the same thing in the magnetic formulation, because it's just effectively the same thing. So I have F wedge star F, which is for the electromagnetism. And the idea is that I have an equivalent magnetic side electric equation of motion and a magnetic side magnetic equation of motion. And so the crucial idea is that because we're working in 4 dimensions, and we're dealing with F, which is a 2 form, I can also construct the Hodge-Joule of F star F. And the Hodge-Joule, if we take in a P form and we're in n dimensions, it gives me an n minus P form. And so 4 minus 2 is 2. And so star F is also a 2 form. And that's where the sort of non-trivial relationship between these two sides comes in. Because if I identify, as I've got here, the magnetic curvature as the Hodge-Joule of the electric side curvature, then what I have is a mapping between the two formulations, but where under the mapping, the classical equation of motion on the electric side, which was produced by performing an Euler-Lagrange equation type setting, is mapped to the Bianchi identity on the magnetic side, and vice versa. So the magnetic side electric equation of motion corresponds to the electric side, the magnetic side electric equation of motion corresponds to the electric side magnetic equation of motion. So these sort of crisscross in terms of the mapping between the two sides. So,
Mark, on the previous slide, you mentioned that the G goes to 1 over G.
Yes.
So how does this relate to this?
At the level of the classical, so when we're doing it purely classically, that does not occur. So if I haven't got any partition function written yet, and I don't have any current or anything coupled to this is just free Maxwell, that does not occur. But on my next slide, I have exactly that. So I can then show that I get this reciprocal coupling. And the way that you actually show this is the crux of Annie's paper, the original bosonic paper. And so what you do is you introduce what is known as a master partition function. And so how this works is instead of having a single field in the path integral measure, we have a pair of fields. So here you can see I've got a 2 form FE and a 1 form AM. And let me move the mouse a bit so you can see it. So what you can see then is I have a particular action there. So this one was well known in the past. And the idea is that under that particular master action, the idea is that I can choose to either integrate out the electric fields or the fields with an E subscript. And what I'll end up with, so you can see, actually I'll do the opposite first. If I integrate out the 1 form A or AM, I end up imposing flatness on the electric field curvature, which at least locally means that my electric curvature is the gradient of a 1 form, which we'll call AE. And that gives me a formulation of electric side electromagnetism. And so this master action by integrating out AM gives me the electric formulation of electromagnetism. But on the other side, I can choose instead to integrate out Fe. And what that'll end up doing is this term here, this cross term, which we call the BF term, ends up imposing a constraint on AM. And the idea is that, I've said this wrong, sorry. So if I integrate out Fe, what happens is these two here act as a Gaussian integral. And this effectively squares this DAM term, giving me DAM wedge star DAM on the magnetic side. And the idea is because these sit from the same formulation, Z in both of these two cases, in the electric reduction and the magnetic reduction, are the same partition function, and so they count as the same theory that I'm describing. But what you can see, to answer that question, is that on the electric side, I have a coupling G in front of the F squared term, But on the magnetic side, I have a 2 pi over g is what it ends up being as the coupling of the magnetic side. And so what's happened is the coupling has become 1 over the coupling. And so then in order to get the proper mapping between the two sides that I have on this.
There's a question.
Oh, go on. Yeah, go on.
Mark, can you hear me?
Yeah.
So the question is in this slide, right? So you're writing a partition function, you have a master partition function, and you're writing it as 2 different ones in the middle and the bottom line, right?
Yes, yeah.
The question is, if you couple this to an external current in order to calculate correlators, can you follow this procedure?
I believe so. So I've not gone about this direction, but I believe that you can do the same in electromagnetism at least. I believe so anyway. Yes. Yeah.
I see.
Cool.
And that's how you get the whistle and 12 towers.
Yes, that's a good point actually. So when we do this, so we have that's a good point. So when we do the actual integral operators that define what are called the magnetic and the electric loop operators of the theory of the Wilson and Toft, as Addy says, we end up requiring actually that is possible, that this works when you have a coupling to currents. Cool. So,
Sorry, just
we'll go, yeah.
there's like a couple of technical things that are hidden there. So, one thing is in the top line, you're treating Fe as a one form, not on its Bianchi identity, and you have a path integral measure over Fe,
I see. Yep.
right?
Yep.
AM is enforcing the Bianchi on Fe, and then you're reducing the path integral measure of Fe to dA.
Yes.
So these are 2 different measures.
Fine. So
So there's a Jacobian factor there to take care of.
yes,
But
in this
equally-
middle line.
Equally, there's Jacobian factors that come from your Gaussian integration. Well,
Yes.
so I wonder if you're doing the same procedure in string theory, that they're actually important. So I was just wondering if you could comment on them.
So at the level of going from the master partition function to the electric, all that happens as you integrate over AM is that this D term, this total derivative, just flips onto the DFE. And so if I'm writing this sort of more formally, I would have a Kronecker delta, not Kronecker delta, the Dirac delta down the bottom, which is holding the constraint that Fe is, or DFE is 0. So you'll see this here is a bit informal because I'm saying that Fe is just dA, whereas actually I can have harmonic contributions as well. And those will be allowed in here, but I'm sort of brushing over that a little bit.
Yeah.
On that.
So you need that.
Yes, exactly. So if I'm doing this sort of fully, I would need exactly that. So I have to, instead of writing, yeah, I would do my delta DFE in this integral measure out the front out there if I'm doing that fully.
And then the second question is, when you do your Gaussian integration, you get a determinant factor.
My Gaussian integration. Yeah, so I'll have a volume out front, exactly. But that will, so at this level, that will be independent of the fields. And so that will not actually introduce any tower of interactions or anything on the action that we're looking at, at least here. It will do later and something that we look at, but not at this level, at the level of just pure 4D Maxwell.
But it does depend on the manifold you're integrating over. Maybe you're just
It would do,
maybe you're
yes,
just
it
in
would do,
R4,
yeah.
I don't know.
Yeah, so here I'm just working in R4 exactly, but in general, that you were right that it would do. All good here? Brilliant. So if I compact on R3 across an interval, I can reduce to 3 dimensions. And so specifically what happens is my 4-dimensional one forms reduce to become 3-dimensional one forms along with scalars. This is the piece on the left hand side. And my 4-dimensional 2 forms become 3-dimensional 2 forms along with scalars as well. And so the idea then is that on the electric side, after we've performed this splitting from the 4D master, will give me the familiar expression for three-dimensional Maxwell theory. So this is the F wedge star F piece on the electric side formulation of the partition function. But on the magnetic side, because I get a scalar, actually I brushed over something, which is that some of these terms decouple and become unimportant in the expression for the action. And so the pieces that remain end up being this two form on the electric side and a scalar on the magnetic side. And so what you end up with is this slightly different looking relation rather than between F and star F. It still is, but it's sort of looking a bit different as you see that now in 3D we have a relation between F and star d phi. So it's a vector scalar duality, they call it. And so another thing is that upon having this, we have to be careful that phi in the reduction is actually a compact scalar. As if it were not, then the electric side would not have proper flux quantization. And so in order to maintain that across the duality, we need that the phi is mapped to itself under a H-mapping circle.
So this is something that's very similar in high temperature field theory. The temperature is a circle with one of the. You also do a complication like this in the reduction. And the phi is interpreted as a not a Higgs field, but as a scalar field with a mass. It gets a mass basically. It's called the Debye mass.
Okay. Yeah.
But maybe not in Maxwell. So I'm just wondering whether your scalar fields, whether a mass is generated for your scalar field.
Not in the case of Maxwell. So it is just the scalar photon.
Right. Okay. It needs to be self-interacting.
You do anti-period.
That's for Fermi.
Temperature is anti-period. Ah, that's true.
Yeah.
But
It's
it generates the mass in here. It's just
Because it's U1 still.
It's a U1.
Okay, it's fine. Yeah.
It's very simple.
Cool. So so just briefly for anyone who's not seen Chern-Simons theory before. So Chern-Simons theory is what we call a topological field theory. Sort of classically, if you study it, it's not particularly interesting in that the equation of motion is just that the field strength is vanishing and you can't really extract anything else from it. However, when you define it fully quantum mechanically inside the path integral, the idea is that the coefficient of the Chern-Simons term, you see k over 4 pi, the idea is that if we require that the partition function behaves properly under large gauge transformation of the underlying gauge field, that this number k here must be quantized, it must be an integer with the current normalization. And so this was a piece of something that people found tricky when trying to find the S-dual of Chern-Simons theory, because people were thinking, well, if surely the coupling ends up in the denominator, this k ends up in the denominator, which then breaks the idea that we require that k is an integer because now we have diffraction. And so actually it turns out that in the U1 at least, that the proper dual to Chern-Simons theory is what we would call the Guyotto-Witten formulation of Chern-Simons theory. And something that's important here is that so there's two fields that you can see that are making up this theory. So we have both A and B. And the idea is that in this setting, both A and B are themselves proper U1 gauge fields. And so it looks like there's too much here because they look very similar. However, this is a proper theory, and we can show that this, if we perform a path integral over B, will land us with the Chern-Simons partition function, which is the same theory then. So on to Maxwell Chern-Simons theory. So Maxwell Chern-Simons theory is just simply what you get if you combine the actions for Maxwell theory with Chern-Simons theory. And interestingly, you end up with something a bit more not just interesting than on either side. So pure Maxwell theory, obviously, you have the massless photon, and in Chern-Simons theory, you just have a topological field theory where you consider that to be massless. But the idea is that upon combining the two, the classical equation of motion is such that you generate a massive vector field. And so we say that the photon has gained a topological mass due to the introduction of the Chern-Simons term, and this mass will be quantized in levels of k. So the mass is g squared k over 2 pi. And then so it looks a bit fishy here, where I've written g squared equals 0, but the idea is that if I delete the Maxwell term, which is the level of a master action is done by setting g squared to 0, I end up with pure Chern-Simons theory, so I only have the topological term remaining, whereas if I set k to 0, I end up only having the Maxwell term remaining, both of which are massless field theories, but what happens is in the interpolation between the two, in Maxwell Chern-Simons theory, I have a proper topologically massive field theory. And then also, this still has interesting phase changes under large gauge transformations due to the fact that we have this Chern-Simons term. So,
Sorry, Mark.
Oh,
can I- your first term is still a 4 form, no?
so
No,
he,
no,
what about so?
no, sorry.
No, the star.
No.
3D star.
I see. I see.
Yeah, so I've got 3 minus 2.
Yes, yes, yes.
4 minus 2.
The first time just F mu nu, F mu nu.
Yes, yeah. So what we have then is what Addy did. So what Addy did is to construct particularly this top master partition function as we saw for the fully Maxwell case, but now for three-dimensional Maxwell Chern-Simons theory. And so what we have there is two fields again. So I've got both AE and AM. Now, this time, AE is again a proper gauge field, and so transforms under gauge transformations, whereas AM, at least at this level, is a non-gauge field, and so it's just a one form at this point. And so what he ended up showing was that if I take, in the case of g squared equals to 0, I can take on the electric side by integrating out my magnetic side. That'll give me at the end of the day this partition function, which is the partition function of Maxwell Chern-Simons theory. And that, again, here, AE is a gauge field, and so it is proper Maxwell Chern-Simons theory. Whereas on the magnetic side, integration is more difficult. And so what we end up doing is effectively completing the square in the electric variables. And upon doing that, you see a natural change of variables that show up, where I introduce a new field B, and this B field is itself a proper gauge field. And the idea is that that removes the dependence on the electric gauge field that still carries the gauge information. And upon doing that and working things out with all the coefficients properly, we end up with what's known as the Desiger-Keefe massive vector theory. So there are sort of two pieces. You see these first two terms and then the second piece. Now, as mentioned earlier, whenever we have a reciprocal K, we should be suspicious because if I have a reciprocal K on a Chern-Simons like term, which wedge dAm looks like, then that would perform or it would change improperly under gauge transformations. But as I said, AM here is not a gauge field, and all of the phase information is updated through this additional B wedge dB Chern-Simons term. Any questions there on that?
This relationship is.
Mark, can I ask you one?
Yeah.
So the reason why I was asking before to couple, say, the master action or any of the electric or the magnetic sides to a current is to be able to calculate correlation functions. You are proposing here, Adi was proposing here, a duality between the electric and the magnetic side, and the best way to test it is calculating correlation functions between both sides. Do you think in this case an external current can be added?
So Addy in the paper very slightly, or he put a section in the paper where he does perform a calculation on both sides to check this, but I've ended up going a different direction in the extension. You
So
can.
you can show that correlation functions of the electric theory and the magnetic theory will have the same result.
Yes.
Endpoint functions of Wilson loops map to endpoint functions of Toft loops under the duality. And that also agrees with the strings, that the fundamental strings goes to a D1.
Did you hear that, Carlos?
I see.
Okay, yeah. So yeah, Andy shows this in the paper with the Wilson and Toft loops. There we go.
And what about correlators of some more local operators? Can that be done? That's what the current would do, right?
Yeah, so in the paper, I don't think that this was done, but I don't see any issues to introducing a current, but I have not done this.
I see. Okay.
Carlos,
Can you tell a bit more about, because this is very interesting what you commented, that when you define AE in the way you define it, the nasty thing of the wrong Chern-Simons level is cured by the field B. Can you tell that a bit more?
Yeah, so the idea is that we have that middle term, the second A wedge or AM wedge DAM term. And so the whole point is that if we say that AM is itself not a gauge field, and we never introduced it as one, the whole issue with having a reciprocal Chern-Simons term is null. It doesn't matter anymore because so the issue is that if you do allow such a term to have gauge invariance, then under a large gauge transformation, the phase will not change by 2 pi or 2 pi times I. And so then the partition function ends up being ill-defined in that situation, or it's not mapped to itself again. And so
when I go from the measure in the middle equation, going from integrating over the electric A, and then I go in the second line, integrating over the magnetic A and B, this integration of the magnetic A, does it have any characteristic? Because I have a gauge field on one side, that's AE, there is B gauge field on the other side, and AM that doesn't transform directly.
Exactly. So AM doesn't transform, but it carries the dynamics in the center. Well, once you apply the equations of motion. So the idea is that AM carries the actual excitations. So if we perform find the classical equation of motion of this object, we will get that AM is itself a topologically massive vector. And so what you have is that the magnetic side carries the same dynamics as the electric side, whereas the B fields carries the gauge information of the electric side.
I see. Thank you. Adi was saying something, I interrupted him. I don't know.
He said don't worry. Sorry.
So you can write this formula down. A equals B minus 1 over Ka.
Yeah.
You can write it down. But you know, AE is a connection and a bundle, and B is a connection and a bundle. So what exactly are you doing mathematically here?
So the way I think about it is I'm completing. So if you go to the master partition function, I'm essentially completing the square in the electric variables. And so what that's doing is I'm repackaging these two terms. So I'm managing to disconnect the two pieces. So you see here that AM is connected or is interacting with another field.
And this is my question. I understand algebraically.
Yeah.
That's fine. My point is geometrically, what are you doing here? You're taking a connection, you're saying it equals another connection, plus something that isn't in the category of connections at all. It's just a different sort of object. So I find it a little bit confusing geometrically how to interpret this. And it's sort of related a bit to the next point you made, which is, we don't need to worry about 1 over K because this AMDM isn't a gauge thing, it's not really just. Yeah, I mean, obviously you've got a completely non-covariant term there, AM wedge star A, and what happened in the first instance. But I just find I'd like to know a bit more what the geometry is that you're doing here.
So I don't quite understand the question, but so all I'm sort of saying is that I'm repackaging let's say the magnetic side so that I have like two different. I'm decomposing my magnetic field, let's say, so that I have one half that I understand is carrying all of the gauge shifts that are implemented by the electric side, and that's the extent of what is actually going on. So my magnetic field is simply, a set of 3D vectors, whereas then if my electric side wants to sit as a 3D vector and perform a gauge transformation. So if I perform some change, the idea is that this piece B is just the part of the magnetic side which is absorbing that shift of information or the shift of field values.
So
I guess with the mathematician's head on,
Yeah.
I don't understand what that equation is because AE isn't a really nice thing for a mathematician.
but they transform the same way, the two sides. That's exactly the thing. Under a gauge transformation, they transform the two sides the same way because B is a gauge field, A is a gauge field, but AM is not. So it is invariant under the gauge. So physically, but there's something like
you're adding apples and oranges, is what I'm saying.
No, that's right.
The left-hand side is connections. The right-hand side is connections plus something that's not a connection.
It is okay because you can add something which is gauge invariant to it's okay. Now, let me explain what happens.
I understand the algebra. That's not my point. My point is, what's the geometry that you're doing there?
I'll answer better. What is the physics? So, and I think actually Mark said it. AM includes two pieces of information, a gauge field and something which is not a gauge field. And the two pieces actually captures nicely in the magnetic side. There is the part which is just a massive vector, which is non-gauge. There is a part which is topological. And what the magnetic theory does for us, it decouples the two pieces. So the physics of Maxwell-Chern-Simons is the following. It is Maxwell-Chern-Simons is a theory of a massive vector, right? Just a massive field. But suppose that you flow to the infrared. And in the far infrared, what remains is just a topological gauge field, the Chern-Simons, because the massive decouples. What the magnetic theory is kind of does it in a different way. It decouples the two kind of the fields AE is actually has two things in it in the Maxwell-Chern-Simons. I think so. I didn't answer your question. I answered a different question, but I think more interesting. It's the physics of what's going on. Mathematically, I'm sure it's okay, but I don't know. I mean, mathematicians will be maybe will be nervous at whatever. You can add to a connection a constant piece. Probably. I think it's fine.
I'll move on there for now. There are two special cases to talk about that end up showing themselves as a result of writing that master partition function. So the first idea is that in the case of k equals 0, the change of variables that we've just done cannot be done anymore. And so, but that's not an issue because what ends up happening is that the dependence on the electric side configurations end up not appearing in the same way. And so I can actually perform the integral over the electric side, which is where the delta that we have here comes in. And so this here is exactly the scalar photon or the dual photon. And then in the case that G squared is 0, we have this, or we end up with this Guyot-Witten formulation of Chern-Simons theory again. But to continue on that point, that this field AM is at this stage not itself a gauge field, I have to then reintroduce its gauge dependence by thinking of it instead as a gauge field, but where up to this point, I've been eating all of the gauge dependence of this object through another scalar field called a Superspace field phi, such that under a gauge transformation, both the now gauge dependent field AM and the Superspace field phi transform in a way such that A minus d phi, which is what we had as AM before, was a gauge invariant quantity. So now the idea is that we can consider Maxwell-Chern-Simons to be a reduction, not just of the Chern-Simons piece, but I should mention that the theta term, so a term that we can add to electromagnetism, upon dimensional reduction with proper boundary conditions, this will reduce to become Chern-Simons term. Now, the minimal amount of supersymmetry, if we're going to go in the supersymmetric direction, that we can add to four-dimensional Maxwell plus theta is n equal 1 supersymmetry, which is 4 supercharges. And the theory in 3D, which has 4 supercharges, is n equal 2 supersymmetry. And so that is where we started to add the minimal amount of supersymmetry that was natural to add, at least. We can still get n equal 1 in 3D, but we started with n equal 2. And so that was the first goal, was to just supersymmetrize Addy's construction. So, before I do that, go ahead.
Sorry, the theta term on the top line, is it depending on the position? Is it dependent?
Yeah, so this will be a step function if we're doing it properly. So the idea is that upon the reduction in the, let's say, x3 direction, this ends up giving me a Kronecker delta, and so the f wedge f term will end up reducing to an f wedge a term, if I think of f as dA.
So there, if it's a heavy side, will there be an integration by parts that will produce a delta, a localized thing?
Yes, exactly.
I see. I see. Okay.
So we can also then look at Maxwell plus theta, but in the non-abelian. And so the idea is that in general we have S-Duality at a much sort of more complicated level. And so specifically here, if I'm working in the non-abelian, then I am required that the groups of the electric and magnetic side are what are known as Langlands joules of one another. And so this turns out to be subtle. You can't just jump in and do this for any gauge group G. Particularly, groups have a property known as a lacing number. And the idea is that this lacing number is easiest to deal with, or this particular duality is easiest to reconstruct when the lacing number is 1. Specifically because if the lacing number is 1, then a group's Langlands joule is itself, or it's the same gauge group, or it's the same group. And so what we do is we restrict specifically to the UN, because this is the easiest way around taking the first step towards a non-abelian reconstruction of what I did. So, for those who've not seen any supersymmetry before, I don't want to dwell on this at all, but just to quickly have shown people what this looks like. So, well, the way supersymmetry, the way I'll introduce it is that we have coordinates, x as in usual space, and then we have what are anti-commuting Grassmann coordinates, so these thetas and theta bars. And the idea is that this defines a larger structure called superspace, or these are coordinates on superspace. And the idea is that we can generate our 4 supercharges using this set of anti-commutation relations, and we realize those anti-commutation relations between 2 particular covariant derivative operators. And so the way I want you to think about it, at least at this level, without getting too deep into it, is the idea is that supersymmetric multiplets or fields are essentially generalizations of the fields that we were dealing with so far. So you can see I've got this vector multiplet V, and inside this I have the old bosonic gauge field A. And the idea is then that these other sets of terms are other pieces that point in various directions of superspace. The same thing works with W. So W is the supersymmetric expression of my field strength. So you can see here that I will have a ton of other components, but the idea is that this dMAN is my field strength FMN, let's call it. And then just for completion, I have this what's called a chiral field, which takes the role of the Stuckelberg, or I need this omega to construct the equivalent of the Stuckelberg field. So instead of actually reducing from 4D down to 3D, it turns out it's easier to instead reconstruct each of the terms that Adi wrote in the bosonic master action and simply upgrading them to their supersymmetric counterparts. And so instead of just integrating over 3D space, I'm now integrating over 7-dimensional superspace. So I've got 3 x coordinates and then my 4 theta directions. And so each of these terms, what we did is we promote these to their supersymmetric equivalents on the right-hand side. And that's all that you really need to do. So we don't actually promote the Maxwell term because the Maxwell was not part of the master construction, this F wedge star F term, that was a result of having integrated out the magnetic side. But the idea is that when you actually lift such a term to superspace, it looks like a W squared term. And so when we see that, you should recognize that as the supersymmetric extension of the Maxwell term. So that's what this looks like. So this is the abelian supersymmetrization of Adi's work. And that is essentially what we have there. So every time you update the supersymmetric counterparts.
So the question,
Oh, hello.
is in Witten's, in Cyber Witten, they do superspace Busherization like you outlined right at the
Yeah.
beginning. Is this just the dimensional reduction of that? So there's what you call a master action.
Yes, yeah.
Is written in n equals I don't know.
No, I see. No, so what we did was not that in the end. So that ends up being more complicated than it looks. So what we instead did is we took each of our 3D pieces and then pushed them in the supersymmetric directions rather than starting in the 4D supersymmetric situation and then descending. Exactly. So in the bosonic, it's different. So in the bosonic, it's relatively simple to start in 4D and then step down, whereas in the supersymmetric, it ends up being quite difficult to do that. So we tried doing that, ended up trying a different approach, which was to start with Adi's bosonic formulation and then introducing the supersymmetric counterparts to that, let's say.
In principle, it should work.
It should work. So it can work. I think so. The issue was that there were some boundary conditions that we needed to consider and some complication, and so it ended up just being that this is the way we went about it, rather than it's not necessarily that it's impossible to do that, but it's just not the way that we ended up presenting it. Cool.
Mark,
Hello.
can I ask you one?
Of course.
Can you go a couple of slides back?
Yeah.
Because now I think I understood something.
This one here.
One more.
Oh, this one.
Let me see. Yeah. So they are the vector multiplet. Tell me if this is an important point. You are not taking it in the Vesumino gauge.
Exactly. Actually, this is a good point. So because each.
Then you are going to add the omega field.
Yeah, exactly. So if you see in 2 slides later, here actually you see it. So do you see I have my V minus lambda term?
Yeah.
So the idea is that V specifically is not actual, so without the dash is not in the West-Semino gauge.
Right.
However, I can always choose to present it that way. But the idea then is that my lambda eats up that degree of freedom. And so I can always express the non-West-Semino gauge parts of the V dash through lambda.
I see. And this is kind of analog to this thing that Daniel was complaining about, right? The shifting a connection by a non-connection.
No, that was slightly different. So the complaint before was, I'll jump ahead a little bit, is on this slide. So this would be the supersymmetric equivalent. You see the first equation there? So the idea is that if the complaint was that VE in that expression is a gauge field, and so is B. I see that sort of clarifies it now, actually presenting it this way, because here VM and lambda are, so that might actually answer the question.
Indeed.
That's a good point. Yeah, so I'll speed up a little bit. So where am I? I was done that bit. So again, there's two special cases. So well, let me do the electric side first. On the electric side, we get supersymmetric Maxwell-Chern-Simons in the bosonic here with full n equal to supersymmetry. Mass is as before, and then in the case of G squared equals to 0, the integration follows a little bit differently, but I end up with, again, n equal to supersymmetric Chern-Simons theory. So, on the magnetic side, we end up with essentially the same story as in the abelian theory, where I perform this change of variables, now where Vm and lambda are expressed, as Carlos was asking there, in terms of their proper gauge transforming behavior, let's say. And I end up with this first two terms giving me my non-gauge Desargues action plus a decoupled Chern-Simons term. So then the special case is that for k equals 0 on the magnetic side, I end up with, again, the now supersymmetric dual photon. And that is actually, or we can perform a shift of our variables inside the magnetic gauge field and the Stuckelberg, such that the interesting part when I'm considering Vm as the gauge field is actually carried by the Stuckelberg. So this omega dagger omega that you see here, you should think of in the bosonic as being like a d phi wedge star b phi. So I'm going to press on. To summarize that, just quickly, in the abelian, in n equal 2, we have that for non-zero G squared K, I have Maxwell-Chern-Simons on the electric side, and then I have a decoupled Desargues cross Chern-Simons plus Chern-Simons theory on the magnetic side. For G squared equals to 0, I end up with Chern-Simons theory at level K, whereas the magnetic description ends up with the Gay-Otto-Witten formulation of Chern-Simons theory. For k equals 0, I end up with the familiar formulation of Maxwell theory. And then on the right-hand side, I have the dual photon, the scalar description of three-dimensional Maxwell theory. Something I shouldn't now talk too much about, but is the idea that for the massive case, so where G squared and K are both non-zero, we can actually perform a mapping between field configurations on the electric and magnetic side. And so we're able to jump between each formulation as we want to. One more thing just to have shown it. So if I expand the results in terms of the supersymmetric fields or the components of the supersymmetric fields that I wrote a couple of slides ago, the idea is that, at least in the massive case, we can do this in the two different massless cases as well, but for the massive cases, the actions look like this. So you can see there's quite a lot of terms, and you have on the electric side, we have the gauge field A, scalar phi, and then two fermions inside lambda. And then on the magnetic side, we have non-gauge objects. So we've got phi dash, two fermions, chi dash, and then there's two components in there, and then A dashed. And then on the bottom, I have the actual gauge-dependent Chern-Simons term in n equal 2. So that's what that ends up looking like. So what this has shown is that the partition functions that are defined by these two actions are equivalent to one another. We reduce to n equal 1. Just to have done that, and it's not too interesting. So the way that you perform this reduction is you take the n equal 2 vector theory that we've written and split that into an n equal 1 vector plus an n equal 1 scalar term, and this actually factorizes and gives us a pair of partition functions. And the idea is that the n equal 1 vector behaves exactly the same as the n equal 2 vector did, and the n equal 1 scalar is simply just, at least in the massive case, a massive scalar duality. And that's what we have there in the n equal 1. So to move to the non-abelian, so this is probably the most like sort of more novel part of it, is we upgrade all of our fields to become UN valued rather than just numbered or numbers. And so there's sort of two key points here is that now well, obviously we're taking our fields composed out of matrices, but in order to construct the non-abelian field strength, well, the crucial point is that W's we had at the field strength depends on V in a way that is now very non-linear, whereas before it was completely linear. And so what this does is what you'll eventually see is when I perform a change of variables, this ends up massively complicating things because then I'll have a series of interactions between the new B field, let's call it, on the magnetic side. Something similar happens with this V dash term, the piece that had its gauge dependence eaten in the abelian case. So the idea is that I need both my field strength and my V dashed, as we're calling it, to transform covariantly rather than invariantly in the non-abelian setting. So this is the new parent action. This should look identical other than factors that are changed due to choices of trace normalization to the abelian master partition function, or the action at least. And so each of those terms now are matrix value fields rather than, or UN value fields rather than just numbers. So the electric side follows effectively identically to in the abelian case, where upon integration out of the magnetic fields, we end up with now non-abelian Maxwell or Yang-Mills Chern-Simons theory. Whereas before, if we took the, well, in the abelian case, this was Maxwell Chern-Simons rather than Yang-Mills Chern-Simons. And similarly, for G squared equals 0, we form a partition function, it looks a bit different, or the act of doing that is a bit different, and we end up with non-abelian n equal to Chern-Simons theory in G squared equals 0. So that's almost identical to in the abelian.
So Mark, in the previous slide, and so now it's non-abelian. So now all these fields are also self-interacting.
Yes, yeah.
And so, very naive question when you say just integrate out the magnetic fields. This is essentially doing the whole path integral.
The whole path integral,
So
exactly.
how do you how much time did you spend on board?
That's very simple. So this takes 10 seconds
really?
to do this bit. The other side is the hard bit. And the reason is that this here is sort of quite simple in this expression. And so the dependence on the magnetic field on this for this action is effectively identical. And so Adi did the hard work there in constructing that in the abelian case. Let's say this is going to follow through the same way.
No, but is it okay? I'm just, I'm thinking always about, not always, but sometimes in QCD, you cannot integrate out the gate.
Fine.
So what is the trick that now you can do it? This is also because I know nothing of supersymmetry, etc., etc.
It's not particularly to supersymmetry.
It's A mu J mu still.
Well, what?
It's A mu J mu. So you integrate A mu.
It's still linear in A.
The term that you need to integrate
I
out.
see.
So yeah,
The other way is difficult.
Okay.
yeah. So integrating out the electric side is very difficult. Is the point there? I'll rush on with it because I'm more conscious of time. That on the electric side works the same. Now, as I was alluding to, so due to the non-linear dependence of the field strength on the field that is generating it, I cannot simply write W of x plus y if x and y are two fields that are being acted on as W of x plus W of y. I have to have a non-abelian interaction term. We'd expect that this vanishes in the abelian limit. And so I went through and computed this, which is a little bit ugly, but it's quite simple at the end of the day. All that's going on is I'm producing or I'm expressing these W's, W of x plus y, W of x, and W of y, in terms of their integral representations, and then just computing that integral. And that ends up with this nested interaction term. And so what I want you to focus on is the fact that each of these terms would vanish if I took the abelian limit, and so this will properly reduce to the abelian result from Addy's paper if we take that case. So we perform the shift anyway, and so what we'll end up with is something that looks like the old Desert Chern-Simons piece, but now that I've split the interactions off, we have a second set of terms that have been introduced in this non-abelian setting. In this, well, here I have it from the massive case. Now, specifically, there's two terms that are new that have turned up in the non-abelian. We have this one piece, which depends entirely or factorizes in terms of the interaction between different field strength terms. And then there's this other piece which does not depend on I. And so, sort of naively, you'd expect that this term remains for whatever reason in the abelian limit. However, upon the abelian reduction, this term actually turns into a total derivative. And so we can reformulate the action simply at this level if we're thinking about it as an abelian reduction of this non-abelian version of the massive partition function. So there are a few special cases. This one is not as interesting. So the g squared equals 0, I'll go quickly, is very much at the end of the day, like in the abelian setting. So what we have is that the dual to Chern-Simons theory we can reformulate as a non-abelian version of the Guyot-Witten formulation of Chern-Simons theory. There's a little bit of a subtlety in how we remove the dependence on the Stuckelberg in the fields there. As I was sort of alluding to in the abelian case, it's a little bit more complicated in the non-abelian, but it is doable. And so we end up with the dual to Chern or non-abelian Chern-Simons in the magnetic side. But the sort of more interesting case is for k equals 0. So on k equals 0, we would expect that on the electric side, we have just three-dimensional Yang-Mills theory, which is a lot more sort of raw. And so on doing the, or setting k equals 0 in our master partition function, we still do end up with a flatness constraint on the magnetic fields. However, the issue now is that flatness depends on the electric field configuration for any given electric field configuration. So what you can see here is I have this interaction term. So I've got, say, I require that lambda E of some combination of the magnetic field is 0. But with this label E, this dependence only came in the non-abelian. And in the abelian case, this was then something that is independent of any given electric field configuration. And that is what allowed us to actually perform the path integral in the abelian case with k equals 0 to get the dual photon. But now in the non-abelian, we cannot reasonably perform an integral over the electric side simply because of this horribly nonlinear dependence of this flatness constraint on any given magnetic field configuration. If we try to, so the closest we can get to expressing something nice is what you would call a principal chiral model. And so that would be what the action looks like if we were to treat it somewhat semi-classically. But the issue is that if we're looking at this properly, that in the path integral measure, we have this horrible operator, which then will perform, an infinite stack of perturbations away from this particular action. And so we cannot sort of reasonably claim that that would be the partition function hasn't done anything wrong here, but you can't look at this action in isolation, is the idea there.
Mark?
Oh, hello. Hello.
Mark?
Yeah.
Sorry. So the question is the following. So I understand what you are explaining, right? These non-linearities, etc.
Yeah.
Here you're integrating over gauge fields, right? Should you not fix a gauge that in the non-abelian case, all the Faddeev-Popov story will come quite complicated? Is there any gauge fixing for this SUSY case?
So here we don't perform any gauge fixing. So if you choose, so actually there's this interesting thing where if you Well, so it ends up making things almost more complicated to do this, and so this is the reasonable distance that we went in a sense.
But then to make sense of these path integrals, right, one needs to choose a gauge, right?
Fine. So to think of it that way, then what you could say is that you can't really understand this path integral as actually representing this principal chiral model. This is just what you would sort of naively think prior to treating it in sort of a proper way.
I see. What I'm saying is that the path integrals, to begin with, not even in this case, but in the previous ones, they should also come with their ghost and etc. Right?
Fine. Yeah.
Because the ghost in this case do not decouple from the gauge multiplet, right?
Fine. Yeah. So
it's equivalent to what we are doing, I think. So you're imposing the flatness,
yes. Can you hear that, Carlos?
and then you get the determinant, which is, I mean, it's equivalent to what Carlos is suggesting from the ghosts.
Fine. Can you hear that, Carlos?
Yeah.
And in both cases, it is an answer to the question why Hanani and Witten didn't do non-abelian
Yeah, I see.
in their paper. It's exactly that. The k equals 0 is the pure gauge, and they didn't discuss what happens when you put multiple branes on top of each other, because probably Witten knew that it's going to be messy.
Yeah. So there's not much traction you get past this statement, at least that we've gotten to.
Yeah, I don't know how to simplify it further.
Yeah, I thought about this for quite a long time actually. I couldn't get to it. This is the furthest I got with this presentation.
Another question, yeah, because this is touching with what Hert was asking before, right? Suppose that instead of doing it in the SUSY case, you say, I'm going to do the paper of Adi, but non-abelian. Is that
Yes, fine.
possible? I mean, is it possible to make the integrals?
So the only thing that happens that's different is that this interaction term ends up being this sum is no longer infinite, and so that's the sort of key difference. So there's a combination of the fact that you were requiring, in what I've written here, both n equal to supersymmetry as well as the non-abelian nature. If you do not require supersymmetry and you still require that things are performing or transforming under non-abelian gauge transformations, this interaction term ends up looking a lot simpler. Is the crucial difference.
But still is an interaction, is quartic or cubic, right? It's not something you can integrate.
It's not nice, yeah, exactly. I can't remember the exact form, but it's much nicer than what you see here, but it's still not a particularly. It's not something that I thought I may as well stay on the bosonic for. It's as awkward as.
Thank you.
Okay, sorry,
yeah.
question on that.
Yeah.
I mean, the way you're phrasing it is like, well, it's a calculational choice, right? I can do this calculation or that calculation.
Yes, yeah.
In 4D,
yeah.
It's not actually a choice, right? You can't just say, oh, I'll just look at just bosonic Yang mills and to get duality at the quantum level, you're very constrained, right? You
yes.
To look at supersymmetric quantum. So is it really just a choice in 3D? If you have an exact quantum duality for anything, or is supersymmetry inherently important in this?
I don't think at this level it was, at least up to the n equal 2, because we can just simply reproduce. I don't see any I don't know in this formulation of any reason why we cannot do the same just simply with the bosonic. Yeah, that's,
so there is a good answer on string theory. In the S-duality of n coincident D3 branes, you start with n equal 4 and you end up with n equal 4, and there is absolutely no choice here. It's rigid. Now, when you reduce to 3D, what do? You put NS and a tilted 5 brane. Now, this is how you get the 3D theory, non-abelian, abelian, whatever. Now, the amount of supersymmetry is dictated by the relative angle between the fibrils, and you can reduce, you can have S-duality for various amounts of supersymmetry. So while reducing to 3D, you get as a bonus control over the amount of supersymmetry.
Cool. So to finish off, so basically this is pretty much everything I'm saying. So to conclude what was done in the paper, what we've done is taken Addy's bosonic formulation and effectively extended it to the non-abelian n=2 scenario. And so what we have is an exact equivalence between the Yang-Mills Chern-Simons with n=2 supersymmetry and its magnetic dual in each of the cases of g²k not 0 and g²=0, with that awkward subtlety in the non-abelian of what happens on the magnetic side for k=0. For the very end, I will just quickly say what I've been up to since putting this out. So the idea is that what we have is what was done was that in the UN case, the extension from the abelian example was relatively simple in hindsight, but also that was the easiest place to start, because this BF term, as we're calling it, so this AM wedge DAE piece, or I'll show you on this. So I go back to here. This middle term, the dash MWE, this is relatively simple to have constructed in the UN as a generalization of Addy's bosonic abelian equivalent, let's say. But for the case where we're working with non-simply laced groups, then such a term is more awkward to construct because of the fact that the non-simply laced groups have differing Lie algebras in general, specifically for the case when it's thing called the lacing number is 2. And so what I've been working on since then is taking this UN example and using it to embed two smaller different groups within that, so that I get a duality between the SO2n+1 group and the SP2n group. And that is where I'm at the moment, at least, with things.
All right, any questions? So, quick question.
Sorry, it took a while.
So you talk about S-duality. You have an idea of what the entire duality group is?
For the full,
This Chern-Simons plus Maxwell theory that you have.
so as in the
As in-
set of allowed
Electromagnetic. Is it SL2Z or?
So, as in, so what this is possible to get to? Is this the question? or-
Yeah, like you have S-duality you talked about, then there is like a T-duality that they both generate some larger group. Or...
Fine, but I'm only focusing on S-duality at the moment. So as Addy's been alluding to, there's sort of string theoretic perspectives that we can take to understand this, but I've been sort of fully working in the view of quantum field theory instead of doing any string theory to do this.
I guess in 40, maybe Demetrius' point, in 40, you get shifts of the theta angle and coupling inversion, and
Fine.
together those generate
Bigger
a
bands.
larger.
We've not yet considered this, so yeah, I see what you're saying there.
But I don't know what shifts the theta angle would descend to.
Yeah.
Well, shifting K.
There's also a question
Hello?
from Carlos.
Yeah.
Sorry, Mark. Okay, let me ask very quickly, and because now the students I was expecting, they're here.
No problem.
So, in this S-duality, this is maybe related to what Dimitris asked. So here you work with a group UN, right?
Yeah.
But maybe one expect that the S-dual to be not UN, but some UN over Zn or some variation of that. Is there anything you can see that is telling you what the dual group needs to be?
So the as in so at the level when we were setting out, you mean like why?
Yeah, no, I understand that you start with UN, right?
Yeah.
That's SUN, Carlos.
SUN.
SUN is dual to SUN mod ZN, but UN
Exactly.
to UN.
How okay, so that will not happen in this case. So if you are starting with UN in order to have UN on the other side.
Yes, yeah. So UN, the way to see it is that in order for it to count as an S-duality, the two groups on either side need to be Langlands duals to each other, and so the Langlands dual of UN is just UN.
Okay, very good, very good. And the other is in this 3D, there is one anomaly that plays many times a lot of role. That is the parity anomaly. Is there any subtlety here introduced by that?
Not that I've come across.
see.
So
Okay. Thank you.
no problem.
Thanks very much.
No problem. Are there any more questions? Oh, sorry.
Quite lower died, so
Yeah, thank you for
let's thank Mom.
Thank you.
So you.